Our next speaker is Alessandro Pinto from the International Food Policy Research Institute, and he will talk about predicting future land degradation and its economic effects. Alessandro, you have the floor. Tell us about the future.
Thank you, Mr. Chairman, and thank you all for coming here. Let's see if I can go. So the work that I'm going to present today is actually a continuation of the work that we started about 2 years ago, and that was summarized in the booklet that Nicholas just presented. And it's a continuation because last year we're mostly interested in sort of identifying the drivers of land degradation. And as a continuation, I was interested in seeing if we could create a tool to predict future land degradation. And so this work shows some of the results. I just wanted to thank two people here. I'm presenting the work, but Akiko Aruna and Tinju Zhu are the people who worked very hard to put together the data set that's underlying the analysis. So yesterday we heard two distinguished speakers mentioning how land degradation occurs at time scales that make it difficult for politicians, for people first to realize that it happens, but also that to devise policies that are supposed to combat land degradation. And at the same time, we have heard several times that prevention might be less costly than restoration. And so, in this spirit, as I said, the purpose of this study was to create a tool that would be able to predict future land degradation and would allow us to prioritize action. And also, I wanted to make a connection between land degradation and climate change. Most of my work right now is on the climate change area, and so I wanted to see if we could create a reasonable connection between the two subjects. The first thing we did was scouting the literature and look at what lots of scientists have worked on, and see if we could find agreement on the drivers of land degradation. And on the physical side, for the physical drivers, there is some agreement on the effect of, say, rainfall intensity, slope, wind, and so on. While as you move towards the socioeconomic side of the story, socioeconomic drivers, the agreement sort of disappears, and there are studies that prove one fact and exactly the opposite. These drivers, this list of important factors that are supposed to influence land degradation, are the building blocks, basically, of the econometric model that we have put together. So, for our study, we use the normalized difference vegetation index, NDVI, and as a proxy, both for land degradation and land carrying capacity. We are fully aware of the problems that come with using NDVI. They're very well documented. At the same time, if one wants to sort of work at the global level, NDVI still is the data set that allows you to do that. Because it's a very rich data set, repeated observation across decades, and it covers both spatially and temporally the whole globe for several times. At the same time, the question remains: is it a good proxy for land degradation? So we're aware of that, and I think that there are a lot of people who are already working on this topic, and more work needs to be done in terms of creating this link between NDVI and land degradation. Our approach, it's a very simple econometric model. So we use as a dependent variable, so the thing that we're trying to explain is actually the maximum value NDVI. So we observe, we have 24 observations each year of NDVI. We take the highest value, and then we average across the years this average value for 5 years. And then we use, as opposed to what we did before, we use cross-section data. So instead of trying to explain the change in NDVI, we explain the NDVI value. In doing so, I mean, this allows us actually to have a richer data set. When we try to do that previously, trying to explain the change, there is a problem with the availability of data, especially going back in time. Well, instead we use the cross-section data, we have a richer data set, and we have a higher explanatory power. So the model is a simple OLS, a quadratic form, to address some non-linearities. And we have location-specific sort of variables and also country variables that we're using. So as I said, the model has a global data set. We have, as explanatory variables, we use both climatic, geophysical, and socioeconomic variables. That basically we try to match in our explanatory variables as much as possible the list of drivers that we found in the literature. We try to control for agroecological zones. We try to control for irrigation areas. Irrigation will affect the volume in NDVI observed, so we control for that. We also control for potential spatial effects by basically selecting observations and not including in our estimation the observations that are contiguous. That basically should remove, supposed to remove the spatial correlation in the error term. This is the list of variables that we're using for our model. We have precipitation, rainfall intensity, a proxy for rainfall intensity, average temperature, slope, soil organic carbon, population density, access to market, GDP growth, input usage, some sort of agricultural intensity kind of measure, rules of law, and infant mortality rate to capture poverty. And these are some of the results. As I said, it's a quadratic form, so I'm not showing all, because we get very crowded, it would make for a very crowded table. So here I'm reporting only the first ordered terms. And in the signs, there are some agreements with expectations, and there are also some signs that would deserve some more exploration. But what I wanted to point out here is our R-squared, which is a very respectable R-square. We're basically capable of explaining about 70% of the variation in NDVI volume. So we're quite pleased with that. So what do we do with that? Once we have estimated our parameters, we use the parameter estimates to make projections into the future. So we take the values for our explanatory variables for 2050, projected value for 2050, and then we follow the logic that if the prediction of NDVI is lower than it was in the year 2002, 2006, that would mean some sort of change in, negative change in land carrying capacity or land degradation. And we use, as our timeline, 2050, we use two global circulation models, Cicero and Miroc. They vary in terms of changes in total changes in temperatures and total changes in precipitations. So we wanted to get one very sort of dry type of projection and one more sort of wetter type of projection to sort of enhance the differences, the possible differences across climate models. These are the variables that we use for our projections. So we have predictions basically for precipitation, rainfall intensity, temperature, population density, GDP growth rate, use of inputs, and mortality rate. While at the same, so these vary into the future, while slope, soil organic carbon, access to market, and rural law stay constant. We don't have data for that projected into the future right now. We might have it for soil organic carbon. We're working on that. And these are some of the results. So first of all, this first map shows the decline in NDVI, predicted decline in NDVI, when basically you keep climate constant, so basically you have the same climate as we have now, and that we only let socioeconomic variable to vary. And so you see some areas of high, sort of relatively high drops in NDVI, predicted NDVI, those red areas, if you can see them. And when we also allow the climate variables to change according to our predictions, we start seeing some more significant changes in land degradation. Basically, some of the areas, including the climate change, exacerbates some of the land degradation. And this is for Mirak on one of the 2 GCMs, and this is for Cicero. So they're different. You see spatial differences in sort of the in the changes to be expected, because these, while the climate models are similar in terms of total change in temperature, they change quite dramatically in terms of spatial distribution of precipitation. And we wanted to see if we could say something in terms of the effect of food security. So we included in our analysis sort of estimated the global sort of production, calorie production from 16 major crops, and we look at their output in terms of calories, so we can combine them, and then we look at the largest decline in NDVI. Anything that is greater than the average sort of drop of NDVI, we consider that a hotspot for land degradation. And we also consider it sort of the best land. So whatever land that is greater, that it has higher than average production capability. And this is the map that we get when we look at Mirak. So these are the hotspots in terms of high land degradation and on high productive area. So these are basically 116 million hectares that would be affected. The current output for that land is about $60 billion US. And when you look at Cicero, you have something very similar. It's 105 million hectares that would be affected for land that is currently responsible for 54 billion US dollars. I just wanted to point out the differences, the spatial differences between the two models. I don't know if you can see. According to one model, the United States, Brazil will be heavily affected. According to the other model, India, Bangladesh will be more affected. And there are some areas that are sort of common across the models. But this makes for completely different stories, okay? It's very important to take into consideration. We also don't know if, looking at considering the hotspots for land degradation, if sort of looking at the, whatever it's below, I mean, it's greater than the average change is the correct way to look at hotspots for land degradation. So we also repeated the analysis for changes that are greater than 10%, so where the drop in NDVI is greater than 10%. And it gives different results, as you can see. So now the total sort of productive area affected will decrease from 13 million hectares, and for Mirak to 15 million hectares. Just wanted to give you a sense also. We used our predictions to look at sort of effect on food production, but there are greater implications of land degradation, obviously, that needs to be considered. And just to give you a taste from how sort of these predictions could be used, I looked at some maps for biodiversity hotspots. This is a sort of work that's done by Conservation International. So these are sort of areas in which there has been decline in biodiversity. At the same time, there's a high richness of biodiversity. And we overlay our prediction of sort of land degradation over these hotspots for biodiversity. And you can see, for example, that there are quite a bit of overlapping areas. And if one of the objectives for decision makers is to address or to keep into consideration land degradation, land degradation and biodiversity, this would be, I think this would be a very useful sort of tool. So let me conclude. So I think we made one step, although imperfect, but one step towards a predictive tool of land degradation and including climate change in our consideration for land degradation. Part of the result is that substantial food production areas could potentially be affected by land degradation. It's not surprising, but it might be that what we predict in terms of the effects of land degradation are different from where land degradation is occurring now because of the climate change. Climate change appears to exacerbate land degradation in certain areas, and we need a lot of work to connect these results, NDVI results, with reality on the ground in the spirit of work done recently by BioFlag and others. They're doing fantastic work in sort of looking at the actual meaning of NDVI and land degradation and connected at a more tangible level. And I just want to close with making a call for a close collaboration with scientists of different disciplines, because this is the only way we can make progress. Thank you.
Well, thank you very much, Alex. These were fascinating, original new results. Any quick question? Please go ahead.
Thank you very much, Mr. Chairman. I am from South Africa, Klaus Kellner, and I look at these global maps, and often I get confused and I get worried. Is it not because you have data, very good data from certain regions, that you will get, that you can implement it in your global maps? If we, for example, look at Africa, the African continent, it seems to me that there is no food security problem in West Africa, because I couldn't see it maybe from behind here, but because I didn't see any red spots in the global map. Although previous speakers have mentioned it. But because you have a very good data set from South Africa, and we have a very good remote sensing and NDVI and the institute at the CSIR, we get a very good data from Southern Africa, but maybe not other countries in Africa. And that is why I'm a little bit hesitant often to look at these global maps.
Thank you. Wait a moment, there was another question. So, are the hotspots only showing up where the data are good and you gloss over the rest of the areas? Go ahead. Madam? Microphone.
Thank you. I'm Grace from Nigeria. Just like the question you just raised now, I was wondering where is Africa in the scenario you just showed us. I want to ask if the model you use can be adapted, especially for regional and national assessment of land degradation, knowing fully well that climate change scenario has variability across scales, especially given the dynamics of socioeconomic variables that we can have within the nation across local communities. Is it acceptable to adapt the model he has just presented for regional and national analysis? Thank you.
I think we have another one.
Yes, thank you for the exciting presentation. As models and their outcome and their reliability depend very much on coefficients, could you, or was it possible to perform a test on the model, that's to say, to apply to older NDVI data and to check whether the results of these forecasts match with the observed results from the 2002 to 2006 period?
Okay, let me address the first two questions with one answer. So, in terms of the global data sets, we use basically the data that is available globally. So the problems might be inherently in what the countries report to the various organizations that collect this data. So that is a potential problem, you're right. But the point here is, that I want to make is that this is just one first step towards this type of global analysis. This type of work needs strong ground validation. And it can be enriched with data sets that come from countries. So this is just one step in that direction. What is important to me is that I wanted to show that we are moving to a point where we have tools to address this at the global level. Although, as I said, needs some quite a bit of groundwork. In terms of the validation that you were talking about, we have tried that, and I didn't bring the results. And the problem is, as usual, is in the data, because we tried to basically backcast, sort of going from 1990 to 2000 and see if we could recreate some of the existing maps of land degradation. And we did, but we haven't carried out an analysis to see statistically the kind of result that we're getting. So that is in the pipeline of the research that we're doing. We want to make sure that our results are at least consistent with what we know about current land degradation, which is not an easy in itself, because we know that there are several sort of